A century ago, the Milky Way galaxy was the entirety of the known universe. We had no idea what made the stars shine, and only one star, our own sun, was known to harbor any planets. Of the multitude of those planets, humans had explored only one, the Earth. In 1610, Galileo Galilei pointed his first telescope to the heavens, and he discovered congeries of innumerable stars, hidden in the band of light called the Milky Way. That day, our cosmos grew exponentially. Roughly 3 centuries later, the cosmic bounds exploded once again, when astronomers were able to build telescopes big enough to show that the Milky Way is just one of many island universes. Soon, they learned the universe was expanding, with galaxies retreating from each other at ever-accelerating speeds. Since then, ever larger telescopes have shown the observable universe spans an incomprehensible 92 billion light-years across and contains perhaps 2 trillion galaxies. And yet astronomers are still left wondering how much more universe is out there beyond what they observe. In today's video, we will be exploring the depths of astronomy in our universe, how big the observable universe is compared to Earth, black holes, dark matter, and so much more. How big is our universe? Roughly 15 billion years ago, all the matter and energy we can observe was concentrated in a region smaller than a dime. It began to expand and cool at an incredibly rapid rate. By the time the temperature had dropped to 100 million times that of the sun's core, the forces of nature assumed their present properties, and the elementary particles known as quarks roamed freely in a sea of energy. When the universe had expanded an additional 1,000 times, all the matter we could measure filled a region the size of the solar system. At that time, the free quarks became confined in neutrons and protons. After the universe had grown by another factor of 1,000, protons and neutrons combined to form atomic nuclei, including most of the helium and deuterium present today. All of this occurred within the first minute of the expansion. However, conditions were still too hot for atomic nuclei to capture electrons. Neutral atoms appeared in abundance only after the expansion had continued for 300,000 years, and the universe was 1,000 times smaller than it is now. The neutral atoms then began to coalesce into gas clouds, which later evolved into stars. By the time the universe had expanded to 1/5 its present size, the stars had formed groups, recognizable as young galaxies. Our solar system was formed 5 billion years ago, when the universe was 2/3 of its present size. This makes it relatively young. Over time, the formation of stars has consumed the supply of gas in galaxies, and hence the population of stars is waning. 15 billion years from now, stars like our sun will become rare, making the universe a far less hospitable place for observers like us. Our understanding of the genesis and evolution of the universe is one of the greatest achievements of 20th century science. Our best efforts to explain this wealth of data are embodied in a theory known as the Big Bang cosmology. The major claim of the theory is that in the large scale, the universe is expanding in a uniform way from a dense early state. Astronomers are not sure, for example, how the galaxies were formed, but there is no reason to think the process did not occur within the framework of the Big Bang. Yet the Big Bang model can only go so far, and many fundamental mysteries remain. What was the universe like before it started expanding? What will happen in the distant future, when the last of the stars exhaust the supply of nuclear fuel? No one really knows the answers yet. Expansion of the universe. Our universe is viewed in many lights by mystics, theologians, philosophers, and scientists. In science, we only accept what is tested by experiment or observation. Albert Einstein gave us the now well-tested and accepted theory of general relativity, which establishes the relations between mass, energy, space, and time. Einstein showed that a uniform distribution of matter in space fits nicely with his theory. He assumed without discussion that the universe is static, unchanging in the large-scale average. In 1922, the Russian theorist Alexander A. Friedman realized that Einstein's universe was unstable. He found that the slightest perturbation would cause it to expand or contract. The existence of an expanding universe implies that the cosmos have evolved from a dense concentration of matter into the present broad spread distribution of galaxies. Fred Hoyle, an English cosmologist, was the first to call this process the Big Bang. Hoyle intended to disparage the theory, but the name was so catchy it gained popularity. It is, however, somewhat misleading to describe the expansion as some type of explosion of matter, away from some particular point in space. In an explosion, the fastest particles move out into empty space, but in the Big Bang cosmology, particles uniformly fill all space. Astronomy from ancient civilizations. It's no secret that ancient Babylonian, Assyrian, and Egyptian astronomers knew the approximate length of the year. The Egyptians from 3,000 years ago adopted a calendar based on a 365-day year. They kept careful track of the rising time of the bright star Sirius in the pre-dawn sky, which has a yearly cycle that corresponded with the flooding of the Nile River. We still use some of these records in studying stars that exploded a long time ago. The Mayan culture. In Mexico and Central America, the Mayan people were able to develop a sophisticated calendar based on the planet Venus. They made astronomical observations from sites dedicated to this purpose 1,000 years ago. The Polynesians learned to navigate by the stars over hundreds of kilometers of open ocean, a valuable skill that enabled them to colonize new islands far away from where they began. Early Greek and Roman cosmology. The word cosmology was derived from Greek origins. Before the invention of telescopes, humans had to depend on the simple evidence of their senses for a picture of the universe. The ancients developed cosmologies that combined their direct view of the heavens with a rich variety of philosophical and religious symbolism. At least 2,000 years before Columbus, educated people in the eastern Mediterranean region knew the Earth was round. The writings of Aristotle, the tutor of Alexander the Great, summarize many of the ideas of his day. They describe how the progression of the moon's phases, its shape-shifting abilities, result from our seeing different portions of the moon's sunlit hemisphere as the month goes by. Aristotle also knew that the sun has to be farther away from the Earth than is the moon, because occasionally the moon passed exactly between Earth and the sun and hid the sun temporarily from view. This event is called the solar eclipse. Aristotle cited convincing arguments that the Earth must be round. His arguments bordered on the eclipse of the moon, the appearance of stars, and the revolution of the Earth around the sun. Dark energy. More is unknown than is known. We know how much dark energy there is because we know how it affects the universe's expansion. Other than that, it is a complete mystery, an important mystery. It turns out that roughly 68% of the universe is dark energy. Dark matter makes up about 27%. The rest, everything on Earth, everything ever observed with all of our instruments, all normal matter, adds up to less than 5% of the universe. An explanation for how space acquires energy comes from the quantum theory of matter. In this theory, empty space is actually full of temporary virtual particles that continually form and then disappear. But when physicists tried to calculate how much energy this would give empty space, the answer came out wrong. Wrong by a lot. The number came out 10 to the power of 120 times too big. That's a 1 with 120 zeros after it. Obviously, it's going to be hard to get an answer. Whether dark energy is a property of space, or a new dynamic fluid, or a new theory of gravity, it remains a total mystery. Dark matter. We are now more certain that dark matter is far from what we originally thought it to be. First of all, it is not in the form of dark clouds of normal matter, matter made up of particles called baryons. We know this because we would be able to detect baryonic clouds by their absorption of radiation passing through them. Secondly, dark matter is not antimatter, because we do not see the unique gamma rays that are produced when antimatter annihilates with matter. Baryonic matter could still make up the dark matter if it were all tied up in brown dwarfs, or in small dense chunks of heavy elements. But the most common view is that dark matter is not baryonic at all, but that it is made up of other, more exotic particles, like axions or WIMPs, which stands for weakly interacting massive particles. Black hole. Black holes are some of the most intriguing, yet not very well understood objects in the universe. which are best described by Einstein's theory of general relativity. One of the more interesting predictions of the theory is that even time will slow down near a black hole. But why exactly? Time slows down near a black hole due to the extremely strong gravitational field of the black hole. According to the theory of general relativity, this phenomenon is due to the gravity of the black hole curving space-time in a way that affects all measurements of time and space near the black hole. But what are black holes? Black holes are points in space that are so dense they create deep gravity sinks. Beyond a certain region, not even light can escape the powerful tug of a black hole's gravity. Anything that ventures too close, be it star, planet, or spacecraft, will be stretched and compressed like putty in a theoretical process, aptly known as spaghettification. There are 4 types of black holes: stellar, intermediate, supermassive, and miniature. The most commonly known way a black hole forms is by stellar death. As stars reach the ends of their lives, most will bulk, many times the mass of our own sun, into such a tiny point that gives black holes their powerful gravitational pull. Thousands of these stellar mass black holes may lurk within our own Milky Way galaxy. The first object considered to be a black hole is Cygnus X-1. Cygnus X-1 was the subject of a 1974 wager between Stephen Hawking and fellow physicist Kip Thorne. Hawking bet that the source was not a black hole. In 1990, Hawking conceded defeat. Before we continue, if you've enjoyed this video, please let us know by clicking the like button. Subscribe to the channel if you haven't already, and turn on the bell notification so you never miss an upload. And finally, the Big Crunch. The Big Bang cosmology implies, however, that life is possible only for a bounded span of time. The universe was too hot in the distant past, and it has limited resources for the future. While most galaxies are still producing new stars, many others have already exhausted their supply of gas. 30 billion years from now, galaxies will be much darker and filled with dead or dying stars, so there will be far fewer planets capable of supporting life as it now exists. The universe may expand forever, in which case all the galaxies and stars will eventually grow dark and cold. The alternative to this big chill is a big crunch. If the mass of the universe is large enough, gravity will eventually reverse the expansion, and all matter and energy will be reunited. During the next decade, as researchers improve techniques for measuring the mass of the universe, we may learn whether the present expansion is headed towards a big chill or a big crunch. For now, the answers to the fate of the universe remain unknown. However, whatever developments the coming decades may bring, we can trust that science will bring us answers about our intriguing universe. And with that, we've come to the end of today's video. If you've enjoyed today's video, let us know by clicking the like button. Thank you very much for watching, and we'll see you in the next video.